That's the way I've been thinking. You know Newton? Yeah, the head fella.
Yeah, the good guy.
Yeah. He's got a first law.
Yeah, he does. I've heard of a second law.
Yeah, and apparently he's got this fourth law about gravispation or something.
Yeah, but we're missing something in between.
We definitely are. I don't know what it is. So let's look again. Let's look again. Find the link.
So there's somewhere here there must be a link between what's in between his second and his graven what nation.
Yeah. So the Michelin Man's really happy.
Oh, I've got it. I've made the link between all of this stuff.
All of it?
Yeah.
Oh wow.
If you drink tea,
right,
while you're poorly,
of course, yeah,
and you don't weigh a ton,
which you don't,
either of them, not the new ton or the old ton.
Oh yes, because you have to take that into account. There's a range there, yeah.
So when you drink tea when you're ill and you don't weigh a ton and you're in sand, it has to be the third law.
Oh, I see what you're saying, Wayne, because when you pour tea on sand, find the Michelin Man goes on mushy and you can only count 3.
Exactly. So we've done it. We have proved that in between the second and the fourth must be the third law.
Yeah. So what's that?
Well, that's a good question.
Thank you, Wayne.
So Newton has a third law.
Yeah.
And we've just arrived there, but unfortunately that's not the bit you need for your exam. So don't worry about how we did that. It's a bit advanced.
Yeah, it's sort of you have to use a special type of clever cracker logic, which is a bit hard to get your head around.
So Newton, he was pretty good with force. He likes his force.
He does. He's pretty much a Jedi.
Yeah.
So I'll say it as we rub things off.
Yeah.
He said that for every time a force is applied to A, sort of like in Wayne's thing, if you apply A applies a force to B, B applies the same force back to A.
This is easier explained with a couple of examples and talking it through. So the law you have to remember is when force A exerts a force on force B exerts a force on force A. But what does that mean?
Well, it's the famous if action every opposite reaction thing.
Yeah. So if I push Triv, Triv's going to go that way. But really, Triv's also going to give the amount of force I'm pushing him with back at me. That's what Newton's law is saying.
Mm-hmm.
So Triv will go flying because I'll have momentum as I go, as I apply the force, and he's a bit lighter than me, so the momentum will push him even quicker. But he will actually be exerting the same amount of force back on me, which is a bizarre thing to think about, really.
But it's a useful concept when you have lots of problems to do with force, such as a ladder against a wall.
Yeah. So what we do is we draw something called a free body diagram.
Yeah, now a free body diagram is when you take the important things in a question and the way they relate to each other, you draw the forces acting upon them. So when you have a ladder against a wall...
Yep, this is my ladder, this is the floor, and this is the wall.
Yeah, it's a very nice drawing, thank you. A bit like a triangle. You have different forces. So your ladder is against your wall.
Yep, so it's going to be applying a force here against the wall into the wall.
But because of Newton's third law, there'll be an equal force going the other way.
Yeah, the wall will actually be pushing the ladder a little bit as well.
Yeah, and the same thing's happening at the floor.
Yeah, it's at the angle of the thing. It's like this.
Mm-hmm.
That's a force there. And so there's going to be an equal and opposite force back along the ladder.
Yeah.
And as you know,
finally,
it's got its weight.
Yeah.
And an interesting thing actually, when things are falling, if I drop this pen, should have done that with the lid on.
Yeah,
when I drop the pen, obviously you know the Earth's pulling it down, it's going to force downwards, but the Earth is actually coming up towards it. Very, very minuscule.
Yeah.
It's pulling it, the pen is pulling the Earth up to it as well.
And you don't notice this because the pen is so small in comparison to the Earth that there's no obvious effect. But it's a bigger effect when you do it with suns and planets.
There is. So what we can say is that in this ladder, there'll be an equal force upwards against the weight because of Newton's law, third law applying. So you mentioned something about the sun.
Yeah, the sun does the same thing to the Earth, and the Earth to the sun, and that causes some crazy dance moves, mate.
It does. The sun is actually like a mini DJ.
It is.
So it's got the Earth hurtling around it.
Yeah, going crazy. But as it's pulling it,
it sort of has little wobbles.
Yes, it is
in the direction.
Like a dubstep. So the Earth wobbles a bit. Yeah, as it's wobbling there. But if the Earth wobbles, then that causes effects on the sun.
So the sun, its flares it'll have like little wobbles around the edges.
Now its wobbles will be smaller, but it will wobble. We can tell something quite cool about that.
If you look at distant stars and you see that they are wobbling, you can see the amount that they're wobbling and see how many planets it has, how big the planets must be, and how far away from the sun the planet must be. And that can be useful because now we can be so accurate. It used to just be big, massive suns that we could observe this.
Yeah.
But now we're so good. I say we, I'm not doing much for it. But they can actually see the tiniest stars, they're not that big.
Yeah,
Big.
they look that big, but that's because they're really, really far away.
But we can see how many planets they have, we can see how far it is away. Now that's useful. If it's close to the sun, it's going to be too hot and uninhabitable.
Yeah.
But we can see habitable planets in terms of temperature from a very large distance.
Which is very jazzy. But anyway, back to our ladder and wall diagram. Now, the first thing I noticed, Wayne, that's quite a busy thing there. There's lots of things going on.
It is indeed, yeah. It looks a little bit ridiculous, and if you were to do this in your exam, you wouldn't be marked down. That is a free body diagram. But when it
It's a
comes to
bit
working it
confusing.
out, yeah,
So what I'd like to do is I'd like to remove some of those things, and you can.
yeah, and this is you'd have been doing it without thinking before
Yeah.
because it would seem obvious.
So when you push your ladder against the wall, your wall hopefully, it won't move at all.
Yeah, your wall's going to be pretty
Rigid,
damn
yeah.
solid. So the force going against the wall from the ladder,
Doesn't make any difference to it.
yeah, we
You
can
can get rid
we
of
just
that.
ignore. It's not going to cause any motion of the wall
And
or
the
any
same
measurable motion.
Will happen to the ground.
Yeah, the ground isn't going to move, so we can just ignore that because in terms of the ladder and stuff and its angles, you're going to be using these forces. And again,
The earth won't be moved up,
yeah,
just like that. So this gives you a much clearer diagram when working out all of your forces.
and then you know you can create your proper vector. We more like here.
Yeah, as the ladder isn't moving, it's in equilibrium, so you have a closed vector triangle, and then you can do things with it.
You're familiar with that.
Yeah,
Your
yes,
AS.
hopefully.
But it's Newton's third law would say these other arrows exist, and you need to sort of take that into account
Yeah,
sometimes.
and occasionally you'll know some arrows because of you'll knowing the ones that are going the wrong way. You don't need to know.
Yeah, exactly. So in terms of equations, so there isn't much you need to do. But you
Yeah.
need to appreciate the fact that there could be these other arrows.
Yeah.
You need to be able to define his third law. In terms of questions, there isn't really anything.
No,
that's-
they're just sort of-
anything that's new.
Be part of lots of other questions, which is what we're going to get into now.
Yep. So we'll see you there.
Absolutely.
I'm so happy we derived a third.